So the last video we discussed why monopolists charge more than marginal cost. But we didn't pin down exactly what price they charge. Let's do that in this video. So let's start mathematically and then we'll do a graphical version. A monopolist has this kind of demand, as we've seen before, this kind of profit function. And the big challenge is that unlike a perfect competition firm, the price that they set depends on the quantity that they choose. The price they face depends on the quantity. Let's have them choose whatever quantity they want by taking the derivative with respect to Q, and we get basically that if we use the product rule, we first take the derivative of that times Q. The derivative of the second term is P of Q, and that's all equal to 0. And this whole thing, as we discussed in the last video, is equal to marginal revenue. This is equal to marginal cost, and so you end up with marginal revenue equals marginal cost. Okay? If you have the exact functional form for these P's for the inverse demand function, you can solve this. So let's do one simple example where PQ is equal to 1 minus Q. Simple demand. And we're going to have marginal cost, or the cost function, be equal to Q. Actually, we can't have it be equal to Q. Let's have it be equal to Q over 2. Okay. Setting this up, we can substitute in 1 minus Q for our price times Q minus Q over 2. Take the derivative with respect to Q, and we're going to get the derivative of this first term is negative 1 times Q. The derivative of the second term is 1 times 1 minus Q. The derivative of this is 1/2. We get that. So this tells us 1 minus 2Q minus 1/2 equals 0. We could write this, if we wanted to, as 1 minus 2Q equals 1/2. That would be writing it as marginal revenue equals marginal cost. And we can solve for Q. All right, so if I add 2Q to both sides and then subtract 1/2 from each side, I'm going to get 1/4. Okay, so 2 times 1/4 is 1/2. 1 minus 1/2 is equal to 1/2. So that tells me the quantity. What's the price? To use that, I have to go back to this equation up here. If I want to sell 1/4 units, I need to set a price equal to 3/4. Okay? And now that I have the price and the quantity, I can figure out my profit. Profit is equal to a price of 3/4 times a quantity of 1/4 minus a cost of Q over 2. My quantity is 1/4 divided by 2. This is equal to 3 over 16 minus 1 over 8, or 1 over 16. Okay? So that's a simple calculation of profit. We can also do this kind of graphically. Okay? So let's set up our demand function like so. And if our demand looks like 1 over Q, then it starts up here at 1. Cost of 1/2. Marginal cost is 1/2. If you take the derivative of Q over 2, you get 1/2. And so that's our marginal cost. If we had perfect competition, we would sell 1/2 units. Okay. If we set a price at 0, we'd sell 1 unit. So I'm going to erase this thing here. We're not going to set the quantity equal to 1/2. We've seen that the answer is actually 1/4. So how do we represent that graphically? Well, we need to find not price equal to marginal cost, but marginal revenue equal to marginal cost. And the marginal revenue curve is PQ, and we have to take the derivative of that. So PQ is equal to 1 minus Q times Q. Okay, which is equal to Q minus Q squared. And so if we take the derivative of revenue with respect to quantity, we get 1 minus 2q. So this line here has slope 1 minus q, so 1 minus 2q is going to intersect here at the 1/2 point instead. Okay. Okay, so this dashed line is my marginal revenue curve, and where that equals marginal cost, that tells me the quantity that I should use, which we said was going to be 1/4. And then to find the price, I go up to see what is the price I need to charge to sell 1/4 of a unit, or 1/4 units, and we got 3/4. Okay? It turns out that this is kind of this example with these particular numbers works pretty well for lots of cases. Okay? If you have any linear demand, so a linear function would be one where inverse demand has looks something like this, A minus BQ. Revenue is going to equal P times Q, which is going to be equal to AQ minus BQ squared. And you're always going to then have, if you take the derivative of this, so this is our revenue equals to PQ with respect to Q, we get A minus 2BQ. And you can see that basically whenever you have linear demand, they're convenient to draw because they're lines that have the same slope as that look the same as demand except with twice the slope. Okay, so in general, when I have to draw a solution, I can draw any kind of slope I want. There's one that doesn't have a slope equal to 1, very obviously. And if I want to find, and I can put my marginal cost anywhere, so say it's all the way down here. Okay, marginal revenue, I need to find the point on this axis that's about halfway. So I'll say maybe here. And I draw a new line from there to there. That's going to have twice the slope. And this gives me a pretty decent graphical estimate of what this thing's going to look like. So where marginal revenue crosses marginal cost, that tells me the quantity. I go up from there to the price. And that tells me basically a rough idea of what the price is going to be graphically in any model. So the last thing I want to talk about is you can maybe see that the two things that really drive the choice of price are the marginal cost. So for example, if marginal cost had been higher, if I moved it all the way up here, I'm going to choose a higher price because I'm going to intersect here instead, and I'm going to end up raising my price. So for a monopolist, what drives price? Marginal cost and the shape of demand, because once you find your Q, you have to go up to find the price. In particular, it's the elasticity that matters. So recall that elasticity is equal to the partial derivative of quantity with respect to price times P over Q. And so it ranges from 0 to basically negative infinity. It tells us it's a measure of by what percent does quantity change when we change price by 1%. If it's 0, then that means quantity never changes whatever the price is. People always buy the same amount. If it's infinite or negative infinite, then a very small change in price has a astronomically large effect on quantity, right? So if you lower the price a little bit, you sell as many units as you want. If you raise it a little bit, demand drops to 0. Okay? And we can see graphically that these kinds of things matter. So, whoops. Let's draw two different demand curves, one with really elastic demand and one with really inelastic demand, but the same marginal cost. So we'll put marginal cost down here. Actually, let's put it like here. And we're going to have the same marginal cost in both of these demand functions. Over here, let's have really inelastic demand. So we'll go like this. And over here, let's have really elastic demand. Okay. So this is our elastic, and here's our inelastic. Okay, both times Q. And in each case, we can get a decent estimate by finding the halfway point on this axis and drawing a marginal revenue curve, which is going to look the same but with twice the slope. Somewhere like here. And where marginal revenue crosses marginal cost, that tells us the quantity. Pretty similar quantity in both of these cases, but the prices are really different. Okay, so this one has a really high price because demand is really inelastic there, and this one has a relatively low price, even though they have the same marginal cost. Okay, I mean, intuitively you can think about if demand is really inelastic, then if you raise the price a lot, you don't lose a lot of sales, so people kind of have to keep buying from you because they need this product. They're willing to pay a lot for it. And if demand is really inelastic, you don't have a lot of freedom to raise the price a lot because you scare off all your customers. So we can lastly see this with some algebra too, or with some calculus. Let's set up our monopoly profit function one last time. Let's take the derivative again. But let's now write this in a slightly different way. So instead of writing p dash q, I'm going to write the partial derivative of p with respect to q times q plus p minus marginal cost. That's all equal to 0. This is useful because remember the elasticity, as I just defined, is defined as so. If we flip this thing around, we can get 1 over the elasticity is equal to the partial derivative of p with respect to q times q over p, which is flipping all those things. And that's pretty close to what we've got right there. Okay? In fact, if we just multiply and divide by p, we can get this whole thing equal to 1 over the elasticity. And now we've got p over the elasticity plus p. This is all equal to 0 minus marginal cost equals 0. And we can see that now the the profit condition really depends on marginal cost and the elasticity of demand, which is the main point. So next I'm going to have you guys do an example.